Good evening, everyone. So, last class we were talking about metal carbonyls. We have discussed the various types of metal carbonyls. We have also discussed the effective atomic number rule, that is the 18 electron rule. So, today we'll start with the nature of the bonding in carbonyl compounds. So, in carbonyl complexes, the ligand is CO. So, today we will talk about how this carbonyl molecule, that is carbon monoxide, and the transition metal, and it bonds with the transition metal. So this bonding is very important, and it is also a very important aspect in coordination chemistry. So why this metal carbonyls are important? It is because these carbonyl transition metal carbonyls, they are very stable. They can also exist in low oxidation states, and that is mostly we have seen, suppose for in the case of nickel tetracarbonyl. So here the oxidation state of the metal is zero. So, and this type of low oxidation state is not possible for the main group carbonyls. So that is why transition metal carbonyl compounds, they present a very interesting class of organometallic compounds. So we know that bonding in heteronuclear diatomic molecules, we have previously learned that they can be presented with the help of a molecular orbital diagram, because the effective nuclear charge, it differs between the constituents atom. The orbital energies are lower of the atom with the higher effective nuclear charge. So here we will look into the molecular energy diagram for CO, that is carbonyl, for carbon monoxide. So if you look into the molecular orbital diagram, so in the left hand side we have taken the atomic orbital for carbon, and in the right hand side it is the atomic orbital of oxygen, and in between it represents the molecular orbital for the CO molecule. So we will consider the valence and valence and electronic configuration for carbon, that is 2s2 2p2, and that of oxygen is 2s2 and 2p4. Now if you look carefully into this figure, you see that the atomic energy is of the carbon, it is placed higher, and that of oxygen, it is placed lower. Now this is because of the electronegativity difference between carbon and oxygen. So oxygen is placed below that of carbon. So similarly, then by joining the appropriate, by the overlap of the appropriate atomic orbitals of carbon with that of the oxygen, we get the molecular orbital for the CO molecule. So it has been seen that for the carbon monoxide molecule, we see that the highest energy occupied molecular level, that is the HOMO, it is a sigma 2p orbital, which is derived from the 2p carbon and oxygen atomic orbitals. So here, and the HOMO for this CO molecule is the sigma 2p, and the LUMO, that is the lowest energy unoccupied molecular orbital, here it is the pi 2p star. So oxygen, we know it has a greater effective nuclear charge, and we see that is why, that is what we are talking about, the electronegativity and the effective nuclear charge, and that is why the atomic orbital of oxygen, they have been placed below that of the carbon. So this is how we can see that. From we can also see that the bonding molecular orbitals, they are all occupied fully, and it result in a triple bond of the carbon monoxide molecule. There also we see that there is an existence of one lone pair which is available in the carbon atom, which may be donated to the metal center during the bonding process. So also the predominant contribution of this molecular orbital diagram of carbon monoxide, it shows that the 2p, this orbital of the carbon, it contributes more to the overall CO molecule. So approximate shapes of these figures, if we see here, this is the synergic bonding in metal carbonyls, and how the approximate shapes for the sigma orbital of the CO molecule, it has been shown here. So we see that the overlap of the end of the sigma HOMO of the carbon monoxide, it overlaps with the vacant d orbital of the metal, and thus the bond is formed. So because of this type of bonding, so we see a high electron density of the metal. So now if we take a particular metal where 6 CO ligands are approaching the metal center. So the six CO ligands, they simultaneously donate electrons to the metal via the overlap of the HOMO of the CO with the vacant d orbital of the M. So because of this donation of the electrons from the HOMO of the CO to the vacant of d orbital of the metal, then there is a formation of sigma bond between the metal and the CO. So thus there is need to delocalize this electron density. So this is achieved by an overlap of a filled d orbital on the metal with the pi LUMO star of the CO molecule. So this, the two orbitals, now after the overlap, they have the correct symmetry to allow for this interaction, and thus the electron density which was more on the metal, it gradually removes back from the metal and it goes and concentrates back to the carbonyl ligand. So this, because of this developing of the charge density of the metal and then again the removal of the charge density on the metal, so this is the whole process, it results in a charge transfer. So this additional bond, we call it as the d pi p pi bond. So the carbon monoxide molecule, it is a sigma donor and a pi acceptor, and the metal is a sigma acceptor and pi donor. So thus there will be a flow of electrons from the CO molecule to the metal through the sigma bonding, and also there is a back bonding possible in such type of systems. This back bonding is a very important it is an aspect of metal carbonyls, and this back bonding is also called as synergic bonding through the pi system in the reverse direction. So this synergic effect, it leads to a strong short, almost double covalent bond between the metal and carbon atoms. So back bonding is a very important case that arises in the case of metal carbonyls. Now, according to the representation of the bonding, electrons would be pushed into the pi bonding orbital of the carbon monoxide molecule, that is the carbon monoxide ligand. So, when there is an increased occupancy in the anti-bonding orbitals, then there is a reduction in the bond order below the value of 3 in case of a normal carbon monoxide molecule. Even experimental results have also found this. But in when we otherly take the case of other ligands, so they can also bond to transition metals, like if we have alkenes or phosphines, but they are not very good pi acceptors as carbonyl, as the CO ligand. So metal atoms in carbonyl complexes, they have very low transition states, oxidation states, which may be negative, zero, or very low positive. Then the first question that arises, why do metal carbonyls, they remain stable in such low oxidation states? Now this has been explained by the sigma bond, which we call it as the concerted bonding effect, which involves the sigma bond between the metal and carbon. So how is this sigma bond that is formed between the metal and carbon? So the sigma bond is formed by the overlap of the sp hybrid orbital of the carbon and the vacant d orbital that is present in the metal atom. So the, suppose we take the example of nickel tetracarbonyl. So in case of nickel tetracarbonyl, the sp3 hybrid orbital of nickel in the nickel, in the NiCO4, we will take the sp3 hybrid orbital of nickel, dsp3 hybrid of, in case of FeCO5, and d2sp 3 hybrid in CrCO6, they have this type of bonding. So similarly, pi bonds are formed when the filled d orbitals of the metals, they overlap with the vacant antibonding orbitals of the carbon monoxide groups. So here in these two cases, the CO to M sigma bond has been represented very clearly. So this, the electrons, they go get into the M from CO to M, and here in the second case we see this is M to CO pi back bonding. So this is the two type of bonding that is possible in metal carbonyls, and that is why the metal carbonyls, they are very stable in the low oxidation states. And this is the, this back bonding is graphically shown in this figure, and sometimes we refer to it as the synergic bonding. So now when we talk of a free carbon monoxide molecule, the electrons are polarized in the direction of the more electronegative oxygen. Now we know that between carbon and oxygen, so oxygen is more electronegative. So that is why in a CO molecule, the electrons are polarized in the direction towards the oxygen. That is, the oxygen develops a slight delta negative charge. So it has been found that the electrons in the pi orbitals, they are concentrated in the vicinity of the oxygen. That is, they are mostly found here in the vicinity of the oxygen and not on the carbon. So when transition metal cation is taken and it forms a compound with CO, so this type of polarization is reduced in the CO bond because it attracts the bonding electron. That is, so for a free carbon monoxide molecule, the electrons, they are pulled or polarized toward the oxygen molecule because oxygen is more electronegative. But when we have a transition metal particularly that is attached to a carbon monoxide molecule, the extent of polarization that was induced by the oxygen because of its higher electronegativity, it is now reduced because the CO bond is now, the carbon center is now attached with the metal central metal atom that is present in the complex. So the electrons in the positively charged complex, they are more equally shared by the carbon and the oxygen. So this results in a strong bond, and so the CO stretch is in higher energy. So simple carbonyl contains CO groups which bonds through CO and not through O. So mostly when we talk of terminal carbonyl groups, then the bonding is through CO to the metal and not to the O to the metal. So we should also remember that CO behaves as a electron pair donor and acceptor through C and not O. So always the bonding is through C. In a carbonyl complex, the bonding is through C and not through O. Even if O is more electronegative in nature, it behaves, the carbon, it behaves as electron pair donor and acceptor despite O being more electronegative in nature. So in general we can say that CO, the carbon monoxide molecule or the carbonyl group, is a sigma donor Lewis base and a pi acceptor Lewis acid. Now, this sigma donation from L to M and pi back donation, here L represents the ligand and capital M represents the metal, and the pi back donation from the metal to ligand is together known as synergic. That is, since both sigma bonding and pi back bonding occurs simultaneously, so this is known as synergic transitions or synergic bonding. So spectroscopic studies have also, they have also indicated that the carbon monoxide is present as a part of the molecule. However, these are for simple carbonyls. But when we have polynuclear carbonyls, they may contain bridging CO because polynuclear means when more than two metals are present. So that is why when we have polynuclear carbonyls, then bridging is possible. So in such type of cases, the sigma bonding is reinforced by additional sigma bonding which stabilizes the complex. So in polynuclear carbonyls, we come across other additional sigma bonds which is required to stabilize the complex, and also they are required to stabilize the low oxidation state of the metal. So many compounds we know that they have zero oxidation states even for simple carbonyls or also polynuclear carbonyls. So the very low oxidation states, they are not found with sigma ligands. Like if we take H2O and NH3, we have suppose we take H2O or NH3 as ligands, then this low oxidation states, they are not possible. Only low oxidation states or zero oxidation states has been possible for metal carbonyls, and this particular feature is ascribed to the presence of d pi p pi bonding, or what we call it as the sigma synergic bonding. So the resulting covalent bond between metal and carbon atoms is not only strong, but it is almost double. So now coming to some important reactions of metal carbonyls. So first is when we have pentacarbonyl iron, when it is heated with an alkali followed by oxidation with manganese dioxide, it gives Fe3CO12. So here in these two equations, you can see what happens when FeCO5 is heated with MnO2. So it takes up the OH minus and Fe3CO12 is formed. So the most important reaction is the formation of carbonylate anion by addition or alkali, as it has been shown in the downward reactions. So if you look carefully in the first equation, that is FeCO5 plus NaOH, it forms an intermediate complex plus Na2CO3 plus H2O. So we see that the reaction of the sodium carbonate with a metal carbonyl, it is basically a nucleophilic attack. That is this OH minus, it's the nucleophile, and it is an attack by the hydroxide ion on the carbonyl group, and therefore it gives a metal carboxylic acid complex. This is the metal carboxylic acid complex which further reacts to form sodium hydroxide and to form a hydrido anion. So then if we have FeCO5 plus a metal in liquid ammonia, then again we see that a sodium, here sodium iron complex has been formed plus CO is liberated. Similarly with different types of metals and their reaction in ammonia, we see different types of, this is a nucleophilic attack has been shown here. Then formation of carbonyl hydride, it takes place by the reaction of metal carbonyls with H2. So when we pass H2, normally we see hydrides are formed when hydrogen reacts with any particular metal. Similarly, the carbonyl compounds, they form their carbonyl hydrides. Like for example, Mn2CO10, it reacts with hydrogen under specific conditions to form the corresponding manganese carbonyl hydride. So here it has been shown. Similarly, for the cobalt 2CO8, its reaction with hydrogen, it forms cobalt carbonyl hydride. So equation 5.23 and 5.24, it shows the formation of carbonyl hydrides. Then another important reaction of carbonyls is the formation of carbonyl halides. So they are formed when the metal carbonyls, they react with halogens. Suppose FeCO5 plus X2, it forms FeCO4 X2 plus CO. So here in this reaction, the halogen here, it reacts with one molecule of the carbonyl of the CO group and it replaces one CO, forming the corresponding carbonyl halide. Now in this given equation, the Mn2CO10 plus bromine, it reacts to form lower carbonyl by causing the cleavage of the metal bond. So in equation 5.26, you see this is a bridging carbonyl where Mn bond is formed, and this is a polynuclear carbonyl. So when it reacts with bromine, then the metal bond is cleaved and the lower carbonyl is formed. Similarly, CO2, CO8 and nickel tetracarbonyl, they decompose in the presence of halogens. That is tetranickel carbonyl, that is NiCO4, it reacts with bromine to give the nickel halide NiBr2 plus 4CO. Similarly, CO2, CO8, when it reacts with a halide, any halogen, it forms the corresponding cobalt halide plus the CO is released. That is, when nickel and cobalt the carbonyls, they are treated with halogens, then the carbonyl compound, they undergo decomposition and the CO group is released. Then the fifth class of reaction is the displacement of CO by other ligands, which are actually substitution reactions. So here for example, nickel tetracarbonyl plus PF3, it forms nickel CO2 PF3 whole 2 plus CO. This is a simple substitution reaction, or we call that displacement reactions. So some of the example has been given here. Here pentacarbonyl iron, that is FeCO5 plus PPH3, this is phosphine, forming iron CO4 PPH3 plus CO. So these are normal displacement reactions which for carbonyl compounds, transition metal carbonyls. Then the formation of nitrosyl with NO, it takes place. So when we subject a metal carbonyl, that is FeCO5, to NO, nitrous oxide gas, then this is FeCO2 NO2 plus CO. Similarly, for CO2 CO8, when it is subjected to NO, it forms one molecule of CO is released and it forms CO CO3 NO. So such type of nitrosyl carbonyl compounds are formed whenever the transition metal carbonyls, they are made to react with NO. Then the action of heat. This is an important category of the reaction of the carbonyls. That is the action of the heat. So the action of the heat, it varies. The product varies for different types of carbonyls that have been taken. For example, in the first case, the pentanickel pentacarbonyl iron, that is FeCO5, at 200 degrees centigrade, it undergoes decomposition to give the iron plus 5CO. But when nickel tetracarbonyl, if you see, it is heated at 180 degrees centigrade, it forms nickel plus 4CO. The Fe2CO9, which is a bridging carbonyl, when it is heated at 70 degrees centigrade at in toluene as the solvent, then we see a mixture of compounds that is formed. So here that is FeCO5 plus Fe3CO2 is CO12. But the same Fe2CO9, when the temperature is changed to 50 degree, then we see different types of products are formed. So this is how the with the change in temperature parameters and the solvent medium during the reaction, so for the different types of metal carbonyls, different types of products are formed. So now coming to the vibrational spectra of metal carbonyls. So vibrational spectra, it is mostly related to the FTIR, that is Fourier transformed infrared spectroscopy. So FTIR is a very useful technique to understand the different functional groups that is present in a particular compound. So when we perform the FTIR experiments, then we get a spectrum. The spectrum is in the x-axis, we get the wave number, and in the y-axis we plot the transmittance or absorbance. Now different compounds, we know they have different types of vibrations. So for they are the molecules, we know that they are not rigid, they are dynamic in nature, and such type of molecules, they have various types of vibrations or different types of motions. So particularly when we talk of vibrations, we have stretching vibration, bending vibrations, rocking, scissoring, and there are many types of vibrational modes. So here, but then we also have symmetric bending, asymmetric vibration, so such various types are there. So particularly since we are talking about metal carbonyls, and of the we are talking about the metal, particularly metals, then they are a special group which shows specific absorbance value or the transmittance value in the FTIR data. So first we will look into the types of stretching for a particular carbonyl. So here in this figure 5.16, you can see the two stretching modes of of the carbonyl group has been shown. The first figure, it shows the symmetric stretching, that is both the this is the metal and two CO groups are attached, and since both the CO, they are pulled in the same direction, then we see that this is a symmetric stretching. But in the second case, we see that the CO are, they are stretched in the opposite direction. So this case is called as asymmetric stretching. So this is how we identify the two different vibrations, that vibration modes that are possible in case of carbonyl. Now, in both the cases, because one is symmetric stretching and the other is asymmetric stretching, both of these stretching modes, they result in a change in the dipole moment of the metal carbonyl. So as the dipole moment is changed, so two bands are expected in the FTIR spectra of a terminally ligated CO molecule. That is, if we have a carbonyl complex or a carbonyl compound, then if that CO molecule is bound to the metal in it by the terminal bridging, then by the terminal bond, then two types of bands are expected in the FTIR spectra. Even the FTIR and Raman spectroscopy, they have been used to determine the geometric of different type of metal carbonyls. So a mononuclear pentacarbonyl, it can exist. Suppose we have a single pentacarbonyl mononuclear, let us say the metal is M and pentacarbonyl is MCO5. So it can exist both in the square pyramidal and TPP geometry, because here the coordination number, since 5 carbonyl are present, so two cases are possible. So one is the square pyramidal geometry and the other is the trigonal bipyramidal geometry. So with the help of this IR and Raman spectra, we can actually predict that among these two geometries, which is the feasible geometry for the particular compound. So that is why IR is important to talk about or to know about the particular stretching frequency of the carbonyl group that is present with the with the metal. Then coming to how the bonding and structural elucidation of carbonyls. So, infrared spectroscopy, as I have told before, this is a very important tool for understanding the structure of any known compound or any unknown compound. And in this class, we will talk about the importance of FTIR spectroscopy in understanding the structures of carbonyl compounds. So the CO bond order and frequency, they are related to its absorption, they are directly proportional. So thus it can be predicted that the frequency of absorption will be of the order, first the free CO, it will absorb at a very high frequency, which will followed by the metal carbonyl cation, then by the neutral metal carbonyl, followed by the metal carbonyl anion. So the stretching frequency for the carbon oxygen bond, it vibrates around 2143 in the gaseous state, and the vibration frequency of carbonyl compound, it lies in 2100 to 1700 centimeter inverse, depending on the structure and nature of the ligands present. So now this region is not having bands that arise from the organic groups. So we will focus the absorption of the carbonyl groups in 2100 to 1700 frequency range. So now let us see if we can validate this synergic model of bonding of carbonyls by this IR spectroscopy. How IR spectroscopy is useful to know the case of the synergic bonding that we observe in the metal carbonyls. So when we talk of the synergic bonding, the bond length and the strength of the CO bond, it would change because the electrons, they are placed in the pi orbital, so pi star orbital. So the bond becomes weaker and longer, thus it vibrates at a lower frequency. Now this matches with the experimental observation when it has been seen that the C double bond triple bond O in carbonyl compounds, they vibrate at lower frequency when we compare the vibration of the gaseous CO molecule. So now when we take a gaseous carbon monoxide molecule, the frequency at which it vibrates, it is much higher than the frequency at which a metal carbonyl that vibrates. So here it shows that the because of certain type of bonding in metal carbonyl complexes, the frequency here it is lower than a free carbon dioxide molecule. So we will let us remember that for multi-electron systems, where we know we will talk about the effective nuclear charge here. So when for a multi-electron systems, we know that s orbitals are the one which penetrate the most because they lie closer to the nucleus and have the highest increase in effective nuclear charge. So the energy of the ns orbitals, it drops much below the corresponding energies of the np or the nd orbitals. But this situation, we this is a basic way of saying that the order of penetration of orbitals is s greater than p greater than d, which is greater than f. But the situation, it changes when the 3d orbitals, they get filled up with some electrons. The 4s orbital, it occupies much space, so it is far more penetrating than the 3d orbital. Thus, the effect of the positive nuclear charge is much more in 4s than that of 3d, and the energy of 4s orbital falls and it becomes more stable than that of 3d. So, now here look into the carbonyls of nickel and CO. So, when we look here, the central metal in both nickel and CO, it has 8 d electrons, that is, it is a d8 system. But the effective nuclear charge, it increases from iron to nickel. So because of the change in this z effective, that is effective nuclear charge, the residual negative charge of the metal is more for iron than for nickel. So as the negative charge on the complex, it increases, the electron density on the metal increases, and so that is why the back bonding is also increased. So as a result, the electron density in the pi star, it increases, and the bond between the carbon and oxygen, it weakens, and thus it vibrates at a lower frequency. So this is how it has been explained. So now, when we see that the IR spectroscopy, so the advantage of using IR spectroscopy to characterize different carbonyl complexes is that because there are only a few observations for other groups in the region of, we talked of 2100 to 1700, and the CO stretching vibrations are particularly the prominent in this area. So particularly in this region from 2100 to 1700, there is no interference from any other organic groups, and any type of carbonyl stretching, they can be observed in this particular wavelength, wave number region. So that is why IR serves as a very important tool, or as a very particular tool for the identification of the bonding or the geometry of the metal carbonyls. So the frequencies of these observations, they give the magnitude of the bonds of the strengths of carbon oxygen bond. So for example, we have FeCO5. Now this FeCO5 has D3H symmetry. Then we see that the vibrational modes, it has only one non-degenerate and the rest are double degenerate. So we expect that the IR spectrum of FeCO5, it should be like this, that it should show two CO stretching frequencies having different intensities. So when we look here, this is the IR spectrum of FeCO5, then it shows the two different types of symmetries. One is for the doubly degenerate, it has one non-degenerate, and the other is the rest remaining the double degenerate. So here in table 5.6, we can see the infrared stretching CO stretching frequencies of different types of mononuclear carbonyl complexes. When we have nuclear tetracarbonyl, we know this is tetrahedral, and the point group here, it is TD. So the symmetric frequencies, they are, this is IR active modes is A1, and the CO stretching mode symmetries has been given here, and the observed frequency is 2125. Similarly, if we take osmium pentacarbonyl, then the structure is TBP and the point group is D3H, and it has been found, the observed frequency has been found in this range. So these are how IR, it shows the different frequencies depending on the metal and its geometry. Now we should also note that this CO stretching frequency is very sensitive to the environment around the metal. So in a metal carbonyl, high electron density is always localized on the metal. So there will be an increase in the extent of back bonding. So once this back bonding increases, the an increase in back bonding means that the electron density in the pi star orbital is also increased. So the bond order decreases and the bond length increases, causing a decrease in the carbonyl stretching frequency. So for example, here it has been given, this is a nickel complex which has three carbonyl compounds attached to it, but the other ligands, that is PME3, PPH3, and PPF3. So you see three different ligands have been attached here, but the other remaining the same. So here in this case, we see the CO stretching frequency is different in the different cases. So what do we see? The methyl groups on the PME3, we know that they show a positive inductive effect. So because of this inductive effect of the methyl groups, the electron density will be pushed towards the metal, so the back bonding increases and the MC bonds here are stronger. So therefore, once the M's metal to carbon bond is stronger, the CO frequency, it will be lowered. So that is why it occurs in a lower region. Now, when we talk of the PF3, now this fluorine molecule or the PF3, it has a electron withdrawing fluorine. So because fluorine is present, which is electron withdrawing in nature. So because of this electron withdrawing group, the electron density which was present in the metal, it is removed from the metal. So once the electron density is removed from the metal, then the pi bonding is also removed from the extent of pi bonding becomes slow. So once the pi bonding is reduced, then the metal to carbon bonds or the CO bonds, the CO bond, it increases or it gains strength. Thus once the CO bond is strong, then it absorbs in a higher stretching frequency. So this is how we differentiate, or we say the stretching frequencies are affected by the presence of the different electronic groups across the central metal atom. So again, similarly, we will see what happens to the higher stretching frequency in polynuclear carbonyl. So this is a simple carbonyl that we talked of. So now we will talk of a polynuclear carbonyl. How does this frequency is affected? So, so let us take the example of the neutral carbonyls. For, for bridging CO, that is the frequency range is 1800 to 1900 for bridging CO and 1950 to 2150 for the terminal CO. So a specific example that can be taken is CO2 CO8 in the solid state, where it shows the higher stretching bands at 1857, 1886 and the different centimeter inverse. Now, so even the CO bond lengths are different for the different types of bonding. So here when we have polynuclear carbonyls, and since because of the presence of different types of CO or the CO bond lengths, we see different types of stretching frequencies. The stretching frequencies of normal CO, they are found in the region 2140 to 1800 centimeter generally. But when we talk of the bridging CO, they have their frequencies in the lower region and they are mostly found to be in the range of 1700 to 1850 centimeter inverse, where the CO group it bridges two metals. So here in table 5.7, you can see the different infrared stretching frequencies of neutral and anionic carbonyl complexes. So suppose we have the metal carbonyl, that is nickel tetracarbonyl, then the stretching frequency, that is nu CO, is 2046. For the cobalt carbonyl tetracarbonyl minus that anion, so here it is 1883. For FeCO for 2 minus, it is 1788. Suppose we have for the MnCO6 plus, it is 2090. For the cobalt chromium hexacarbonyl, it is 2000. And for vanadium hexacarbonyl and anion, it is 1860. So this is some of the new stretching frequencies for neutral and anionic carbonyls. So in this table, the bond order for some complexes, carbonyl complexes, has been shown. For nickel tetracarbonyl, the CO bond order is 2.54. For COCO4 minus, it is 2.14, and for FeCO4 2 minus, it is 1.85. So in the next table, the carbonyl frequencies for the bridging terminal CO bond lengths, it has been shown. So from all this table, so what inference we see, that the metal carbonyl stretching frequency, it will increase as the metal oxidation state decreases. So here what does it mean? Like suppose we have a carbonyl, that is manganese hexacarbonyl plus, then the stretching frequency of metal to carbon, that is new MC, that is the metal to carbonyl, it is 416. But for CrCO6 it is 441, and BCO6 minus it is 460. So in these three cases, if we look at the oxidation state, here it is oxidation state of the metal, it is +1, and so it is 416. Then for chromium CO6, the metal oxidation state is 0, so this is 441, and here this is -1, so this is 460. So we see that the stretching frequencies increases as the metal oxidation state it decreases. So this is one important inference that we have studied from the metal stretching carbonyls, their IRs, from the IR studies. So here the conclusions arrived that on the effect of the formal positive charge on the metal atom is that there is no change in the strength of the sigma bond between the carbon and oxygen as well as the metal and carbon. It is only and particularly the pi electron or the pi electron density that is changed. So the sigma bond between the carbon and oxygen is irrelevant in the case of metal carbonyls. So mostly the changes in the particularly in the electron density or the pi back bonding, so they influence the stretching frequency and other associated factors. So it has been observed that the metal carbon force constants is in isoelectronic, and they are in these two cases and they are almost equal. So the carbonyl stretching frequencies for different the complexes, it has been shown here, but nearly the near quality in the MC force constant and loss is compensated by sigma donation. Now, when we take an IR spectra of a metal carbonyl, we always take it in the vapor phase, that is in the liquid phase, or particularly in a non-interacting solvent, that is hexane. Now, we always take hexane is a very, it doesn't react with the metal carbonyls much easily. So, why do we take a non-interacting solvent? It is because if we take any other solvent which reacts with the metal carbonyls, then we get the corresponding peaks of the reactions of the interactions. So we don't want this. So to avoid any impurities or any unwanted interaction between the metal and the solvent, we always take hexane as the solvent for the IR, for the IR of the metal carbonyls. So also if our metal carbonyl is in a solid state, then we take the KBr pellet. So KBr method, the potassium bromide pellet method, is a standard for solid samples in FTIR. So KBr doesn't couple, or it doesn't absorb the IR radiation, and that is why it is taken as a reference in your solid IR. So whenever we come have a metal carbonyl that is present in the solid state, we will take this KBr pellet method. So pellet means there is a compression machine by which we take a small amount of our metal carbonyl, and then we mix with KBr in the ratio. The metal carbonyl to KBr ratio is 1 is to 20. So mostly much how with we take a very small amount of the metal carbonyl, and then they are finely ground together. So after mixing properly in a mortar and pestle, they are put in it is called as compression machine, where a pellet is by applying under pressure, then a pellet is formed, and this is called it as the KBr pellet method. So as a prerequisite, we should know that the basic principles of IR and its applications, so to organic molecules. Here we will look at some sample IR spectra from simple metal carbonyls. Now here, this is the in figure 5.18, we see this is the IR spectrum of Fe2CO9. So here this is the IR spectrum, you can see. So how can the structure of solid Fe2CO9 be? So how do we infer this spectrum? So we see that it has strong bands in both the terminal and bridging regions. So first we will draw the structure of Fe2CO9. So when we draw the structure, we see it has both terminal carbonyl groups and bridging carbonyl groups. So it can be said that both types of groups are CO groups are present in it. So here first we will try to know the types of CO groups or the which type of carbonyl complex we are dealing with. So here we see there are two high frequency terminal CO bridges, and the bridging CO ligands has they always absorb in the lower energy. We should always remember that the bridging uh, carbonyl groups, they always absorb in the range of 1800 to 1700 centimeter inverse, but the terminal CO, they absorb in the high frequency range, that is from 1900 to 2200 region they absorb. So here we will look, the two bridging COs are almost in same line, and thus here a single band is observed even though the complex has a low symmetry and should show two bands for the bridging CO. So this is the structure of here is for Fe2CO9. So that this is how we infer that this part is for the bridging CO and this part is for the high frequency, that is for the terminal CO. So we can say that both these types are present in it. So in this figure 5.19, this is the IR spectrum of Fe2 CP2 CO4. So this is the structure of Fe2 CP2 CO4. So here between we have a bridging CO in this region, and here are present. This is the group that is indicating for the bridging CO, and it has been they both the two CO, they are overlapped since they lie in the same frequency. They have been overlapped in this region. So here we should always note that the number and intensity of the in bands in the IR spectrum, it depends upon the symmetry of the transition metal complex that we are dealing with. So in this case the local symmetry, so how do we know about the symmetry of the transition metal carbonyl? So here we will first find out the number of the carbonyl groups that are attached to the metal, but the actual molecular symmetry may be dependent on other ligands, which is not important. So in this figure 5.20, the structure of Fe4 CP4 CO4, it has been shown. So here we will just look into the number of the carbonyl ligands that are attached to the center molecule and also the bridging CO. Rather, we will ignore the other types of ligands that are present in the case. So here in figure table 5.12, the number and type of infrared stretching frequencies that is expected for different for some common metal carbonyl complexes, it has been shown here. So from this table, we find out that a more symmetric molecule, it will have less number of bands than predicted. So as the symmetry increases, then the number of bands is decreased. So now, why do the intensity of the bands change when the vibration change from symmetric to asymmetric? So when a molecule undergoes a change in its vibration from symmetric to asymmetric, then the dipole moment of the molecule also changes. So the magnitude of the dipole change, it influences the intensity of the bands approximately. So we see that more intense absorptions, they are observed from asymmetric bonds. So it has also been found that the pi bonding also affect the intensity of absorptions. So here two infrared spectrum for two different types of metal complexes, one in the cis and another is the transform, it has been shown. So the number of bands as well as their width also depends on the type of the medium that we are dealing with. Spectral changes have also been observed for different types of solid like cis trans isomers. Then they have the spectral changes you can see in this type of complexes. So here in this case, we can see the nature of the medium, the types of isomers present, they are also important in determining the CO stretching frequency. So what are CO stretching frequencies and force constants? So the CO stretching frequency, we should know that will try to find the relation between the CO stretching frequency with bond order. So for example, as the electronegativity of R increases for R MnCO5 type of molecules, the CO stretching frequency often decreases. Suppose we have an example CF3 MnCO5, the observed frequency are in this range. But if the R group, that is in this CF3, is changed to CH3, then the observed frequency changes in this in a different order. So the electronegativity of the attached R group in a transition metal carbonyl also affects the CO stretching frequencies. In the second case, molybdenum or oxygen is the, here in this complex, is the CO of the CO is the site for the BF3 attack, when 1:1 complex is formed by adding for this type of complex. So if you look into the spectrum, there are more number of CO absorption band than the product. So here the symmetry of the molecule, it plays an important role and decides the type of the CO frequency that it should be, the complex should show. So in figure, here in figure 5.24, this is a metal carbonyl, and if the L is a organic group which is highly electronegative organic group, and we replace it with a less electronegative one, so more flow of electron density takes place to this CO pi star orbitals. So to understand this, one example has been given, that is rhodium CO16. So rhodium CO16 here, it is four of faces of the octahedron. The molecule, it occurs in the four faces of the octahedron, where rhodium atoms are present, and they have carbonyl ligands bridging three rhodium atoms. So here, if this is the structure of this molecule, so the metal metal bonds, they can be predicted easily with the effective atomic number rule. But from the effective atomic number rule, we cannot distinguish which is bridging CO and which is the terminal CO. So the probable bondings of symmetric and semi-bridging carbonyls, it has been shown here. This is the probable bonding type. So it is common to find polynuclear carbonyls both with and without bridging. So like for example, M2CO10, it does not have bridging CO. So tetranuclear osmium complexes like OS4CO16, OS4CO15, they have also been prepared. Now, if we look into their 18 electron rule, then it is consistent with 4, 5, and 6 metal bonds respectively in the above complexes. So, in osmium CO14, 4 of the carbonyl ligands are weakly semi-bridging and 10 are non-bridging. So, here it has been the structures of three tetranuclear osmium complexes OS4 CO16, CO15, and CO14, they has been shown. So the here we will talk about in figure 5.28 the structures and conventions of Fe3CO12 and Fe3CO9. It has been shown for this type of metal. So here they are bridged, and the osmium complexes, if you look here, they are unbridged. So what happens here is, so this cannot be explained by steric hindrance, but maybe with the size effect. So it is very difficult to, particularly with IR spectroscopy, we cannot actually tell the exact geometry of a polynuclear carbonyl. So most of these studies, to exactly know the geometry of the polynuclear carbonyl, single crystal X-ray spectroscopy or the X-ray crystallography, it has been done, which is very effective in knowing the geometry of polynuclear carbonyls. So with this part, the metal carbonyls part is over. Um, so we'll just take a break of 5 minutes and again resume with metal pi complexes. So now we'll start with metal pi complexes. So in this chapter, we'll learn about the transition metal nitrosyl complexes, the transition metal dinitrogen and dioxygen complexes, and particularly the tertiary phosphinase ligand. So what are metal pi complexes? So the transition the complexes, this is an important metal ligand chemistry where the covalent bonding we know it is taken uh, uh, it occurs when between the atoms of which have this nearly same electronegativity. So that is particularly when we say covalent bond is formed. So in this way it can be seen that most transition metals have nearly the same negativities to that of boron, carbon, or the fifth group elements below nitrogen and the sixth group elements below oxygen. So, therefore, various compounds have been prepared involving bonds between the transition metals and one of these elements, particularly such as metal carbonyls or organometallics. To a lesser extent, we have metalloboranes or the phosphine compounds. So all these have been they are important in bio inorganic chemistry or in particularly the heteroboranes. So the golden rule is that if there is energy difference between the metal and the energy difference between the metal and ligand is not much or they are almost same, then a metal pi complex is formed. That is, in other words, very low energy difference is formed. So very low energy difference the with because of this very low energy difference, the molecular orbital extensions and packing symmetry consideration are the ones that result in this class of metal pi complex. So based on these facts we can say that organometallic compounds can be further divided into three classes. The first one is the metal alkyls and metal aryls, that is the metal carbon bond with only a conventional electron pair sigma bond. Then a much larger group, that is the CO we talked of. The third group is the ligands, where the ligands they serve as a pi acceptor, as the CO it occurs in some type of compounds. So here in the electrons they are donated by the ligand. They are not sigma non-bonding but they are pi bonding electrons. So the ligand they serves as the pi acceptor, that is as well as the sigma donor. So to talk about this, we will talk about
क्लास सरीगला कि?
So we'll start with transition metal nitrosyl complexes. So first we will calculate the number of valence electrons of the NO molecule or the nitric oxide. So nitrogen has 5 and oxygen has 6 electrons. So therefore it is an odd electron molecule because it has 11 electrons in total. So now we will look into the molecular orbital configuration. Here 1 sigma 2, 2 sigma 2, 3 sigma 2, 4 sigma 2, 1 pi 4, 5 sigma 2, 2 pi 1. So here the MO diagram for NO, it has been shown here. This is the 2p3 of nitrogen and this is the 2p4 of oxygen, and this is how the overall representation of the molecular energy configuration it has been shown here. So the molecular orbitals of NO, it can be filled out, it has been filled out and it has been shown here. So here NO molecule, it has a bond order of 2.5. So we see, and it has a very low dipole moment. So nitrogen, we know it has a higher electronegativity than that of oxygen, and so the sigma 2p orbital, it is poorer donor when it is compared to that of the CO. So here NO has a single, we can see that there is a single paramagnetic electron that is present here. So we say that NO is paramagnetic in nature. So what happens is it behaves similarly to that of the alkali metals, that is the group 1 metals. NO, it gets readily oxidized to form the NO plus cation, which is isoelectronic with N2 and has a border of bond order of 3. That is, it implies that N triple bond or triple bond. So therefore, the bonding molecular orbitals of the NO molecule, they are more like the oxygen atomic orbitals, while the antibonding molecular orbitals, they are more like the nitrogen atomic orbitals. So here, if the NO radical is bound to the metal, then we call it as the nitrosyl ligand. If the electron pair can occupy the low-lying metal-based molecular orbital, which are non-bonding, then the nitrogen can function as a sigma p as a sigma donor with a synergy pi bonding. So this is for free NO exist as a stable free radical because of the weak NO-NO bond in the dimer. As an alternative to use the free NO plus, mostly in nitrosyl complexes, NO plus, which is isoelectronic with CO, and it can be used instead of CO in a substitution reaction. So we can also construct NO from CO by adding an extra proton to form the NO plus. So here the NO as a ligand, it can coordinate in different modes. Here it has been shown, this is the linear sp hybridization of the NO ligand, this is the bent sp2 hybridization, and the figure C is the bridging sp2 hybridization of the NO ligand. So this is the three different coordination modes of the nitrosyl ligand. So the conversion of the linear to bent for the nitrosyl ligand, it is considered to lead to that increase in the formation of the oxidation state by +2. So the electron density on the metal is raised, and this will encourage the linear to bent conversion, because in the bent NO, a pair of electrons, they originally assigned to the complex, it becomes a lone pair on nitrogen. So here the electronic structure of NO and its bridging to a metal fragment on the covalent and ionic bonds, it has been shown. This is the covalent model, and this is how the ionic model it has been shown. So for example, the Fe3 plus center in oxidized form of, we know myoglobin, it is an iron which is found in the muscles. It forms a linear NO complex. But on reduction of the Fe2, then the NO it switches to the bent form. So in myoglobin, the Fe3 it is formed in the linear form. But on oxidation, the Fe3 present in the myoglobin it changes to Fe2, and then it acquires a bent form. So on the covalent model, figure 6.3, a linear NO is a 3 electron ligand. So in this case, there is no need to rehybridize. The metal has a single occupied d pi orbital which binds with the singly pied NO to give a Mn pi bond. But a bent NO, uh, it is a one electron molecule. So that is, when we have a linear NO, it is 3 electron ligand. But when we have a one bent NO, it is a 1 electron ligand, such as chlorine atom. So here the infrared stretching frequencies, they gives, when we take the IR spectra, then the stretching frequency it gives the mode of coordination which is similar to that of the carbonyl complexes, that is the terminal NO and the bridging NO. So a derivative of the Vasquez complex is the first well characterized example of your bent nitrosyl ligand. So here iridium complex, it is a derivative of the, this is a derivative of the Vasquez complex, and which was the first example of the bent NO that we have ever come across. So the geometry of the product, it is a square pyramidal with a bent nitrosyl ligand. Here you can see. So here in this figure 6.4, so here you can see how the NO is a bent ligand form it is taken. So let us take L as a ligand. N is the number of attached to the metal M. So a 17 electron LNM fragment can bond to NO to give a bent 18 electron complex, where 15 electron fragment can give rise to a 16 bent complex. So the 16 electron bent NO complexes, they are also not very uncommon. They are also known. For example, these complexes, they are 16 electron bent NO complexes. Here it has been shown here. So the discovery that NO and CO are important messenger molecules in the mammalian brain, because NO and CO are very important messenger molecules in the in the human brain, then the binding of, they are binding to the metalloprotein receptors, and thus with this discovery, the interest in NO, particularly NO ligands, has grown up. So typical nitrosyls together with some preparative routes, it has been their preparation routes, it has been shown here. For the first two cases, they show linear bent equilibria. Equation 6.5 shows that NO, unlike most ligands, they can replace all the COs in the metal carbonyl to give a homoleptic nitrosyl. So here you can see how homoleptic nitrosyls, equation 6.5 and 6.6 to 7, it shows homoleptic nitrosyls. But the last two cases here, in these two equations, here we see the case of the use of stable cation, that is NO plus. It is NO plus is a powerful oxidizing agent, and it is even capable of oxidizing very bulky metals, and this results in higher oxidation ions that usually cannot bind NO. So like CO, the coordinated NO, they can give migratory insertion reaction. So here this is CpCO(N minus), the Ri is given to it, then CpCO(RNO), PPH3, and again it is replaced with PPH3. This is migratory insertion reaction. So there are hardly any complexes with nitrosyl ligands alone. So whenever we, for carbonyls, we see it is FeCO5, but for nitrosyl there is hardly any complexes that only contain the nitrosyl ligand. So other ligands are also present in it. However, a large number of mixed carbonyl nitrosyl compounds, they have been known. So here in this case, FeCO5 plus NO, it forms FeCO2 NO2 plus CO. So these are mixed carbonyl nitrosyl compounds. Even though CO and NO they have comparable properties, CO may be utilized in excess at high temperatures and pressures, whereas NO it can lead to undesirable oxidation. So NO is replaced with nitrosyl fluoride, nitrites, nitrosonium salts. So here how NOCl it has been replaced to form this type of mixed carbonyl nitrosyls. Then transition metal dinitrogen and dioxygen complexes. So transition metal dinitrogen complexes means N2. We know that N2 is isoelectronic with both CO and NO. Although a CO and NO plus, although a number of complexes with CO and NO plus are present, dinitrogen complexes they are difficult to prepare. Dinitrogen complexes means they contain N2 as a ligand. So dinitrogen is a weaker sigma donor as well as a weaker pi acceptor in comparison to CO. So it binds very less weakly. So only good pi donor metals they bind to N2. So here one example of a formation of the nitrogen complex. It has been shown for ruthenium. You can see in equation 6.17 how a 17 and 18 how a dinitrogen complex. This is the first example of the transition metal dinitrogen complex for ruthenium that was reported. So dinitrogen is a strong nucleophile which is shown by its displacement of water in equation 6.9, and it is formed a bridging complex how it has been shown. So the two metals they may be bridged by the dinitrogen molecule as it has been shown here. So in this case this is the N2 that is bridged by the metal on both the sides. So if there is an extensive back bonding in such cases, then the actually the bonding reduces to M double bond N, then N single bond N, then N double bond N. This is how the back bonding results in the change of the bonding of the dinitrogen complexes. So majority of the complexes they have a terminal eta 1 N2 monohepto where bonding is similar to that of the isoelectronic coligand. Sometimes these dinitrogen ligands they bind in side-on mode. Here it has been given. So this side-on mode makes the which was monohepto now it becomes dihepto as here it has been shown on figure 6.8. So here this 6.8 is similar to diheptoalkyne, mostly that we see in F group metal complexes. For the dinitrogen ligand, the IR stretching frequency is observed in the range of 2150 to 1900 centimeter inverse. So most of the transition metals they have been used to prepare nitrogen complexes, and lot of research have been done on their reactivities and coordinating ability. So dinitrogen based metal complexes have been synthesized with a large number of transition metals, and it has been shown here. So you can see in this table the elements which forms mononuclear dinitrogen complexes, it has been shown here. So very few are there which form such type of complexes. So those metals which form dinitrogen complexes, we can see they also form carbonyl complexes. So this indicates that the bonding of dinitrogen and carbonyl they are almost similar. So also we see that the elements like iron and MO which form the active sites in nitrogenase. So here in figure 6.9a, the complex CON2 whole 3 it is shown, which is the first case of the transition metal dinitrogen complex that was prepared using a gaseous N2. So it is also the first case of, and this figure B, this is the first case of the molybdenum dinitrogen complex which was isolated. So in a nitrogen metal complex, other ligands such as phosphines, halides, hydrides, ammonia, carbon monoxide, and even water, they can coexist. The nitrogen fixing bacteria that we call it as the nitrogenase, it is capable of converting the nitrogen to ammonium ions catalytically. So here in this bacteria, the active sites they contain iron, molybdenum, and sulfur. So thus many iron and molybdenum complexes have been prepared, have been used to prepare artificial catalysts. Then the methods of preparation of N2 complexes with different metals. So first is by using gaseous nitrogen directly. So different types of complexes that have been shown here, they have been prepared using directly the nitrogen gas. Then some titanium complexes and fully methylated derivative, they have been titanosine. If this is titanium and this is ferrocene, so such complexes are called as titanosine. So then for titanosine dimer, if it is reacted with directly N2 dimer, it forms titanosine dimer with the N2 ligand. So it is how this is dinitrogen dimer is formed here. Also isopropyl magnesium chloride. Here it reacts directly with N2 to form the complex. So likewise, these are some of the processes by which different we can use directly N2 to prepare dinitrogen complexes. Then preparation from compounds containing chains of nitrogen atoms. So the oxidation of coordination hydrazine. So here it has produced the first dinitrogen complex of manganese. Here we see the dinitrogen complex of manganese. Also, this is one method of preparation of good ruthenium dinitrogen complexes. So if a complex it reacts with N2 to give a nitride dinitrogen complex, it can also be obtained from N2O. So these are the various methods. Also the complexes can be prepared from two nitrogen atoms which are combined together to form such complexes. So these are some of the methods of preparation of the dinitrogen complexes. So then coming to transition metal dioxygen complexes. So here the from the molecular orbital theory, the paramagnetic behavior of dioxygen may be explained. So dioxygen can be written with this type of configuration. The antibonding orbitals we know of the dioxygen, they are half filled. That is, they contain one electron, and that is why two or more electrons can be taken up. And because of this addition of two or more electrons, then the shapes are changed during this process. We have the superoxide, the peroxide, and other oxide ions. So these are the different bond orders and the internuclear OO distances. This is for O2 plus, that is dioxygenyl. O2 is dioxygen, O2 minus is superoxide, and O2 2 minus is peroxide. And here the bond order has been given and their internuclear distance has been shown here. So it has been found that all the different charge forms of the dioxygen molecule, the neutral dioxygen can coordinate with the transition metal and form metal complexes. That is the O2. They can also, it has been shown, it has been known that it can combine with the transition metal complexes or transition metals and form dioxygen complexes. So let us study the common bonding modes of dioxygen in metal complexes. When we take a mononuclear metal complex, this O2 it binds in two different forms. One is the end-on, another is the side-on. So here, first part here you can see this is the end-on mode of addition, and in the B part you can see this is the side-on mode of addition of the oxygen molecule to the metal complex. So particularly when we take off two very common proteins, that is myoglobin and hemoglobin, that involves the transport of oxygen across the body. So here particularly this binding of the oxygen, it involves the transfer of an electron from the metal to the oxygen, resulting in the formation of a superoxide. Here it has been shown here in this method. Now, in dioxygen coordination complexes, the side-on mode it has been seen. That is, in Vasquez type complex, you see this is the side-on mode of addition. That is the presence of the oxygen. So there may be metal complexes containing two metal ions in a complex, and to both which the dioxygen molecule is bonded, so resulting in different modes of bonding. You can see here this is one type of bonding where this is monohapto, here this is bihapto, and also here this is both eta 1 eta 2. So you see how different types of bonding of the dioxygen molecule to the metal complexes can be possible. So metals with different types of binding, it has been shown in this some figure 6.13 A and B. So most of the transition metal ions that has oxidation states, that is from 2 to 6, they bind with oxygen. So in these complexes, the metal ions, they have higher oxidation states than their usual ones. So usually these metal complexes, they are diamagnetic in nature, but paramagnetic metal complexes have been reported too. So these dioxygen metal complexes also contain various types of hard and soft ligands. We know what are hard ligands and soft ligands, and the coordination number also varies greatly from 2 to 8. So this some of the important dioxygen metal complexes. First is the hemoglobin and myoglobin. So they are the proteins that we know they are found in the body and they help in oxygen transport. Now during this oxygen transport in the ring, the iron present in the porphyrin ring of the structure, it changes its bonding and state, and that is how oxygen is carried out throughout the body through the formation of oxymyoglobin or by through deoxyhemoglobin and other such compounds. Then Vasca's complex, it is a trans-chlorocarbonyl bis triphenyl phosphine iridium 1 complex, and it is square planar dimagnetic organometallic. Now, when it by this is the Vasca's complex, it is yellow in color. When it binds to oxygen, then there is a change in oxidation state of the iridium 1. Now it changes to iridium 3, as you can see here, and the color of the complex, it changes to orange, from yellow to deep orange. So this is how the addition or the binding of the oxygen to Vasca's complex changes its coordination number, oxidation state, and also the color of the complex. Then there is another metalloenzyme called as hemocyanin. So hemocyanin, they also transport oxygen, and whenever we talk of hemocyanin, we will always know since that they are copper complexes. So this is a copper histidine complex, and this is the histidine. This is how it looks like, the copper, the deoxyhemocyanin. So once oxygen is added to it, they become oxidated hemocyanin, and this is how the complex it looks like, forming the two oxygen, the dioxygen, it binds to the copper ions in a eta 2 peroxo manner, that is a dihapto peroxo manner. So the best method to synthesize dioxygen metal complexes is to expose the metal ion solution to gaseous oxygen O2. So for this, we can directly bubble our oxygen in gas into the metal solution. So this is known as oxygen activation, and that is why we call them as the synthetic oxygen carriers. So here in this mechanism, the O2 molecule, it attaches to the ion in a irreversible manner, in a reversible manner. But sometimes if the reversible oxygen binding occurs, then the metal ion, it moves to higher oxidation state, and these compounds, they are suitable for further oxidation. So the reaction was done to carry out this reaction. This was done by treating precursor of rhodium 1 complex with oxygen at 3 atm pressure. So first a dark color complex was formed, which indicated the addition of this O2 group into the metal complex. We can also prepare peroxo dicopper complex. Here it has been shown peroxo dicopper complex in many ways. So either by bubbling a solution of the O2 gas or by injecting the liquid ligand. So there are many ways by which we can prepare this copper imidazole precursor and then add oxygen to it. Now let us discuss some routes for the synthesis of dioxygen metal complexes. So the metal complexes of CO3 plus and Fe3 plus, which contain O2, they can be synthesized directly from superoxide and peroxides, like here it has been shown. So for cobalt 3 plus and Fe3 plus, we can directly use H2O2, which is a precursor for providing O2. Even superoxide O2 minus, we can also use it. So it will also give the O2 ligand that will directly attach to this cobalt complex, as you can see here. So now coming to tertiary phosphine as a ligand. So how is this tertiary phosphine? It is a ligand. So first is the phosphine complexes, they do not have, the first thing that hinders is that they do not have a metal to organic carbon bond. So MC bond is absent, and so that is why they are not organometallic in nature. But what happens is the nature of the bonding of tertiary phosphine, they have lot of similarities with carbon monoxide molecule. Now because they have much similarity with the carbon monoxide molecule, tertiary phosphine, they are actually regarded as inorganic ligands or organometallic ligands. So substituted phosphines like the trialkyl phosphines, like we have PR3, PR2AR, PAR3, they are widely used. These tertiary phosphines, they are one of those rare ligands where the electronic and steric properties, they may be changed as per our need by varying this R group. So the closely related, we have trialkyl phosphine, that is POR3, or triaryl phosphines like POAR3. They are all, we also have haloaryl, haloalkyl ligands. So the particular, the sigma donor ability and pi acidity of the phosphines are similar to that of carbonyls. The substituted phosphines as well as bridged multidentate di and triphosphines, which we call it as the DPPE, that is called as di and triphosphines like PH2, PCH2, CH2, PPH2. Here it has been shown. So here they are much easy and they are easily referred to as phosphines, that is DPPE, di and triphosphines. So phosphines, they contain a lone pair on the phosphorus atom, on each of the phosphorus atom, and they form sigma bond from the ligand to d metal and a pi bond from metal to ligand. So similar to that of the carbonyl bond, we know how a carbon monoxide molecule or the carbonyl ligand, two types of bonding are present. One is from metal to carbon center and then back from the metal to the carbon, synergic bonding. Similarly, these, there is two type of bonding that is present in case of phosphines, in phosphines. So each phosphine, it contributes two electrons similar to that of carbonyl, and also the valence electron count is similar to NH3. Phosphines, however, they are also pi acids, but NH3 is not a pi acid. The extent of pi acidity also depend on the nature of the R group. So we see that there are certain properties which are of the phosphines, which is similar to that of ligands, either to that of CO ligand or to that of NH3 ligand. And that is why, because of this property, so they are considered as ligands. So even molecular modeling theory has also the molecular modeling, or that is the computational studies, have also indicated the steric effects of the ligands. So C.A. Tolman, he introduced a pictorial representation of the uh, phosphine ligand. So here the extent to which the different ligands are oriented in space and to each other, they can be find out with the help of a cone. So he considered a cone like structure, and then the extent of the ligands, different types of ligands which influence the cone, it has been found of this order, and this cone angle is called as theta. So here the Tolman cone angles have been reported for various types of phosphine, for PF3, for PME3, PCl3. So this is how the Tolman cones and the structure of phosphines are correlated. So regarding the pi donor and pi acceptor properties, it has been found that the average electronegativity of the three groups that are attached to P, it increases. The ligand becomes a poorer sigma donor but a pi acceptor. Thus, the sigma donating ability of the phosphines, it is inversely proportional to its pi acceptor ability. So we can summarize that phosphines are the electron rich in nature. They are good sigma donors and poor acceptors. But the electron poor phosphines like PF3, they are poor sigma donors and good pi acceptors. So here we'll look into one class of phosphines. They are called as monophosphine. That is triphenyl phosphine, trimethyl phosphine. These are monophosphines. So many of them, they have longer R chains, and also mixed R groups are there like PME2PH. So PME3, then PME2PH, PHET2. So these are also mixed phosphines that we call them, they contain mixed R groups. Sulfonated triphenyl phosphines are examples of phosphine ligands which form water soluble complexes like PH2P meta SO3 C6H4 minus, or we have TPA. So TPA is 135 triaza 7 phosphoadamantane. This is TPA. So this is also which forms, it is a water soluble complex. Aryl phosphines may behave like substituted eta 6 serines. So when PR2 is bridged across a MM bond here while donating to other metal bond. So here in equation 6.38, in this reaction, it shows an application where an intermediate forms and a design of the molybdenum tungsten compound. Here it is an example. So this is the phosphine. Then there is diphosphine. So chelated complex, they form diphosphine, that is DMPE, DMPM. These are some of the common is DMPE and DPPE. So you can see this is the example of a diphosphine complex. So here in figure 6.22 we can see this is the chelated DPPM and this is the bridge DMPE. So these are some of the examples of diphosphine ligands. So chiral complexes, they can also serve as catalyst, and then it is required to provide chirality. So chiral diphosphinoethanes, these are the structures. So we can see phosphines are also, chiral phosphines are also present. So then diphosphines with long chain phosphorus atoms have also been found. So these are large ring diphosphines that have been shown here. Cyclic diphosphines are also present. So here is an example of cyclic diphosphines. Then biphosphones. Here this is two examples. These are called as asymmetric binaphthyls. These are also, they serve as the bridging ligands. This is a asymmetric binaphthyl and this is 1,1-diphosphonoferrocin. So these are binaphthals, but they are asymmetric binaphthals. Then we have polydentate phosphines. So polydentate here, such as here is an example of, particularly one important example of polydentate is the CH2PR2 whole 3. So here these are polydentate phosphines. This is a racemic tetraphosphine that it has been shown here, which is used as a catalyst. Then polydentate macrocyclic phosphines. So macrocyclic phosphines means they have macrocycles, like the one that has been shown here in figure 6.30 A and B. These are macrocyclic phosphines which contain PN or PS donors. Then the phosphite ligand. So when instead of R groups, OR groups are present, then they behave as phosphines and called as phosphite ligands, like POMe3. They are called as phosphite ligands. So here it has been shown here. Then heterocyclic phosphorus ligands. So here some of the common heterocyclic phosphorus ligands in figure 6.31a, you can see different types of heterocyclic phosphorus ligands have been shown. Then is the cyclometallic phosphine complexes. So the phosphine ligands, they which are engaged in H transfer reaction, they give MC bonds, particularly the reactions of PME3, it has been shown, and they give the reaction of the MC bond, that is here it has been shown. So these are, and they form cyclated complex, so they are called as cyclometallic phosphine complexes. Then dialkyl diaryl phosphidoligands. So some of the bridging are PR2 ligands. They can be prepared using these types with the zirconium salts, platinum salts. Here it has been so given. So based on this, we have different types of phosphidoligands, phosphinidine ligands. So we can see the phosphine ligands and the phosphine chemistry, they extend to a wide range. Here in example 6.36, we can see the compounds of P and arsenic with multiple bonds. So here in this an example, we have P double bond P, different types of multiple bonds have been present here. So this is the phosphoalkynes, phosphoalkenes with different types of ligands. It has been shown here. So this is all about your phosphines, the phosphine ligands, and these are the some of the questions that are associated with this. So with this part, we finish today's class. We'll